Imagine this. You're strapped into a spacecraft, hurtling at impossible speeds toward a blazing orange inferno floating in the cosmic void. Your heart is pounding, your instruments are screaming warnings, and ahead of you, just ahead, is a K-type star, a stellar furnace burning at 4,000 degrees Celsius on its surface, with a core reaching 15 million degrees.
Okay, Chowder. You signed up for this. You wanted to explore the universe, but did it have to be into a star?
There's no turning back now. The gravity has you. You're falling into one of the universe's most fascinating stellar objects, and in the next 10 minutes, you're about to experience what no human has ever survived to tell. Welcome back to the Cosmic Atlas, where we journey to the most extreme places in the universe and answer the questions that keep you awake at night, staring at the stars. I'm your host, and today we're taking the ultimate plunge with our favorite space explorer, astronaut Chowder.
Yeah, favorite might be a strong word after today, folks.
Before we dive into this stellar inferno, and trust me, things are about to get seriously hot, do me a favor, hit that subscribe button right now, smash that like button like Chowder's about to smash into stellar plasma, and share this video with anyone who's ever looked up at the night sky and wondered what happens when matter meets star. Your support keeps this channel exploring the cosmos, and we've got incredible journeys planned for you.
And maybe hit that notification bell, because if I somehow survive this, you'll want to know about the next adventure, assuming it's not into another star.
All right, Cosmic Explorers, strap in. Today's question is both terrifying and fascinating. What if you fell into a K-type star? Not our Sun, which is a G-type star, but its slightly cooler, slightly smaller, orange-hued cousin. These stellar objects are among the most important in our galaxy for one crucial reason. They're the most important homes for alien life in the entire universe. But before we discover whether anyone lives near these stars, we're going to discover what happens when you die in one. Astronaut Chowder, are you ready?
No, absolutely not. But let's do this anyway, for science.
For science, and for the 15 million degrees of fusion-powered fury waiting for us, let's fall into a K-type star. First, we need to understand what we're actually falling into. In the grand catalog of stellar classification, that famous sequence, Oh, be a fine girl, kiss me, K-type stars sit in the second-to-last position. They're smaller and cooler than our Sun, but they're absolute cosmic champions when it comes to longevity and stability.
So we're falling into a cool star. That sounds better, maybe.
Don't let the word cool fool you, Chowder. A K-type star's surface temperature ranges from about 3,900 to 5,200 Kelvin. That's roughly 3,600 to 4,900 degrees Celsius. For comparison, the melting point of tungsten, one of the most heat-resistant materials we know, is 3,422 degrees Celsius.
Right, so I'll be vaporized. Got it. Not cool at all.
Exactly. But here's what makes K-type stars scientifically fascinating. These orange dwarfs are absolutely perfect for harboring life on nearby planets. Why? Because they're stable, incredibly, remarkably stable. While our Sun, a G-type star, will live for about 10 billion years total, K-type stars can burn steadily for 15 to 30 billion years. Some of them will outlive the current age of our universe by 2 or 3 times over. In terms of size, K-type stars typically have about 60 to 80% of our Sun's mass and about 70 to 90% of its radius. They're smaller, yes, but they're numerous. In our Milky Way galaxy alone, K-type stars make up about 12% of all main sequence stars. That's billions and billions of these orange stellar furnaces, each one potentially surrounded by habitable worlds. Billions of stars I could potentially fall into. Fantastic. Really makes you feel insignificant, doesn't it? Some of the most famous K-type stars include Alpha Centauri b, one of our nearest stellar neighbors at just over 4 light-years away, and Epsilon Eridani, a young K-type star about 10 light-years distant that astronomers suspect might have planets in its habitable zone. The habitable zone around a K-type star is closer to the star than Earth is to our Sun, but it's also more stable. These stars don't have the violent mood swings of red dwarfs, and they don't burn out quickly like massive blue giants. They're the Goldilocks of stellar habitability, not too hot, not too cold, not too unstable, not too short-lived. So if I were a planet, this would be great real estate. But since I'm a human in a spacecraft about to become stellar plasma, less great. Exactly. Because we're not orbiting this K-type star at a safe distance in the habitable zone. We're not even studying it from millions of kilometers away with advanced telescopes. We're falling directly into it, and astronaut Chowder is about to experience every nightmarish stage of stellar immersion that physics has to offer. You know what? I've changed my mind. I'd like to file a formal complaint with Mission Control. Can we maybe just observe from a distance with really good binoculars? Too late, Chowder. The journey has already begun. Right now, our spacecraft is 10 million kilometers from the star's surface. That's roughly 67 times the distance from Earth to the Moon. At this range, the star looks like a brilliant orange beacon, brighter than anything Chowder has ever seen, but still small enough to take in with the human eye. But we're accelerating, falling, and every second brings us closer to temperatures, pressures, and radiation levels that will redefine the word extreme.
Okay, Chowder. You signed up for this. You wanted to explore the universe. But did it have to be into a star?
47 minutes until the real nightmare begins. Let's see what happens as we approach the stellar inferno. At 10 million kilometers out, we're still in what most people would consider safe space. The vacuum around us is peppered with the sun's solar wind, a constant stream of charged particles ejected from its surface, but our spacecraft's magnetic deflectors are handling it. For now.
Okay, let me run through the systems check. Main engines, operational, life support, green across the board, heat shields at 20% capacity and climbing, radiation shielding, holding steady, but we're already seeing 10 times normal background radiation.
That radiation is coming from the star's corona, its outer atmosphere, which extends millions of kilometers into space. Even from this distance, high-energy photons and charged particles are bombarding the spacecraft at increasing intensity. Let me put this in perspective. At 10 million kilometers from a K-type star, you're receiving about 100 times more radiation than you would in Earth orbit. If you were standing outside this spacecraft without protection, you'd receive a lethal dose of radiation in under 5 minutes. Your DNA would begin to unravel. Your cells would stop dividing properly. Within hours, you'd experience radiation sickness, nausea, vomiting, hemorrhaging.
Really painting a beautiful picture here. I'm feeling super comfortable with this mission now.
But we're safe, for now. The spacecraft's multi-layered radiation shielding, combining hydrogen-rich polymers, lead, and electromagnetic deflection, is keeping the worst of it out. But as we draw closer, that protection will mean less and less.
We've crossed 9 million kilometers. Computer is projecting gravitational acceleration. We're starting to speed up. The star's gravity is getting its hooks into us.
And this is where the physics gets interesting. A K-type star, despite being smaller than our Sun, still has immense gravitational pull. At this distance, Chowder is feeling about 0.001 times Earth's gravity pulling him toward the star. It's barely noticeable, but as he gets closer, that force will increase exponentially. Imagine space-time as a stretched rubber sheet, and the star is a bowling ball sitting in the middle, creating a deep depression. Our spacecraft is a marble rolling down that slope, and the closer we get to the bowling ball, the steeper the slope becomes. Eventually, we won't be able to climb back out, even if we wanted to.
8 million kilometers. Temperature in the cabin is now 28 degrees Celsius. That's actually pretty comfortable. I've been in warmer subway stations. Enjoy it while it lasts, Chowder. In 30 minutes, you'll be begging for the subway. As we pass through 7 million, then 6 million kilometers, the star begins to dominate the view. What was once a bright point is now a glowing disk, its surface roiling with convection patterns, massive cells of hot plasma rising and cool plasma sinking, creating a granulated texture across its face. It's actually beautiful. I can see darker spots on the surface. Those must be star spots, like sunspots. And there are these bright regions, active areas where the magnetic field is going crazy.
Those star spots are areas where the star's magnetic field has become so twisted and concentrated that it actually inhibits convection, cooling those regions to a relatively frigid 3000 Kelvin. The bright areas, called faculae, are where magnetic field lines have broken through the surface, heating the plasma to even higher temperatures. 5 million kilometers now. The radiation detectors are screaming. We're receiving 1,000 times more radiation than in Earth orbit. The heat shields have ramped up to 40% capacity. The cabin temperature is now 35 degrees Celsius.
Okay, now it's like the subway. The subway in summer with no air conditioning. And the air smells like... is that ozone?
That's ionized oxygen, Chowder. Some of the radiation is getting through, ionizing the air molecules inside the cabin. It's a sign that our shielding is starting to struggle. Great, that's exactly what I wanted to hear. The shielding is struggling. Fantastic news. 4 million kilometers. 3 million. The star now fills half the view screen, a massive orange sphere of seething plasma. Its surface appears to pulse and shift like a living thing breathing with the rhythm of nuclear fusion. And we're falling faster now, not just from our engines, but from gravity pulling us down into that stellar abyss. 2 million kilometers. We're passing the point where solar flares could reach us. If this star decides to burp out a coronal mass ejection while we're out here, then several billion tons of magnetized plasma moving at 1 million kilometers per hour would tear through this spacecraft like tissue paper. You're really good at the whole reassurance thing. Has anyone ever told you that? We're entering the danger zone now. 1 million kilometers and closing. This is where things start to get genuinely apocalyptic. Okay. We've just crossed 1 million kilometers and every system on this ship is losing its mind. Radiation levels are off the charts. I'm talking 50,000 times Earth background radiation. Heat shields at 70% and climbing fast. Cabin temperature is 45 degrees Celsius. At 1 million kilometers from a K-type star, you're no longer in anything resembling normal space. You're in the star's domain now, its sphere of absolute influence. The solar wind here isn't a gentle breeze, it's a hurricane of charged particles moving at 300 to 800 kilometers per second. These particles, mostly protons and electrons stripped from hydrogen atoms in the star's corona, are slamming into the spacecraft's magnetic deflector shields with enormous energy. Each impact releases a burst of radiation. The deflectors are creating their own miniature auroras around the ship, curtains of light in green and red, as particles spiral along magnetic field lines, shouting over alarms. I can see them. There are lights outside the viewports. It's like the northern lights, but they're everywhere. The entire ship is wrapped in glowing plasma. That's your radiation shielding doing its job, Chowder, but it's fighting a losing battle. At this range, you're being bombarded with X-rays and extreme ultraviolet radiation. If you were exposed directly to this environment, your cells would be delivered a lethal dose in under 1 second. Your cells would be annihilated at the molecular level. But it's not just radiation. The heat is becoming unbearable. The star's thermal radiation, photons carrying infrared, visible, and UV radiation, is pouring into the spacecraft. The heat shields are essentially massive mirrors, combined with ablative materials that vaporize to carry heat away. But they can only do so much. Breathing hard. 52 degrees Celsius in here now. I'm sweating through my suit, the air tastes metallic, and the computers are starting to register errors. The electronics are overheating. 800,000 kilometers. The star now fills the entire forward view. You can't see anything else. No stars, no darkness of space. Just orange plasma, roiling and churning in cellular patterns hundreds of kilometers across. It's hypnotic, terrifying, beautiful in the way a tsunami is beautiful when it's about to crush you. Chowder can now see individual features on the stellar surface with incredible clarity. Granulation cells, convection currents where hot plasma rises in the center and cooler plasma sinks around the edges. Each cell is roughly 1,000 kilometers across. For scale, that's about the distance from New York to Orlando. Mesmerized despite fear. I can see there are loops, massive arcing loops rising from the surface. They're glowing brighter than the rest of the star. Those are prominence loops, structures where the star's magnetic field has trapped plasma, forcing it to flow in arcs tens of thousands of kilometers high. The plasma in those loops is heated to over 1,000,000 Kelvin, hotter than the visible surface beneath them. You're looking at magnetic field lines made visible, twisted and tangled by the star's rotation and convection. Panic rising. We just lost the secondary deflector array. Radiation is spiking, 70,000 times background radiation. The main computer is running at 93 degrees Celsius. It's going to start having catastrophic failures. 600,000 kilometers. The gravitational pull is now noticeable, about 0.01 Earth gravity pulling Chowder toward the star. If he dropped something, it would appear to fall forward toward the view screen. The spacecraft is accelerating faster now, drawn inexorably into the gravity well. Our velocity is increased from a few thousand kilometers per hour to over 20,000, and it's increasing with every second. The star's gravity is relentless, patient, and absolutely inescapable.
500,000 kilometers. Cabin temperature is 61 degrees. The heat shields are at 90% capacity. I can hear them groaning, actually hear them through the hull as they ablate away. We're losing mass. The outer layers of the heat shield are vaporizing, carrying away thermal energy in the process. It's the same principle that keeps spacecraft from burning up during atmospheric re-entry, but scaled up to stellar proportions. Atoms of the shield material are being ripped away by the heat, forming a thin trail of debris behind the ship. 400,000 kilometers. 300,000. Communication with Earth would be impossible now. The intense radiation would scramble any radio signals, and the star's magnetic field would induce massive interference. If Chowder wanted to call home and say goodbye, he's missed his chance. 200,000 kilometers. The star's so close now I can't comprehend the scale. Those granulation cells, they're each bigger than Earth. Bigger than Earth, and there are thousands of them, millions, all churning and boiling like some cosmic ocean of fire. The temperature has reached 78 degrees Celsius. Chowder is drenched in sweat. Every breath feels hot in his lungs. The spacecraft's cooling systems are working at maximum capacity, but they're designed for deep space, not for flying into a star. They're failing. 100,000 kilometers. Heat shields at 98%. Cabin temperature 85 degrees Celsius. I'm getting warning lights across the entire panel. Primary systems failing. Backup systems engaging. Tertiary systems preparing for emergency protocols that I'm pretty sure just mean pray. 100,000 kilometers from the stellar surface. This is where we cross a threshold. This is where we enter the star's actual atmosphere, the corona. And this is where the true horror begins. We're inside the atmosphere. I can feel it. The spacecraft is shaking. There's resistance now, like we're moving through something thick. Welcome to the corona, astronaut Chowder. Welcome to the outermost layer of the star's atmosphere, where physics becomes utterly counterintuitive and reality bends toward nightmare. Here's the thing that blows scientists' minds about the corona. It's hotter than the surface beneath it. The photosphere, the visible surface of the star, sits at roughly 4,000 to 5,000 Kelvin. But the corona, this tenuous outer atmosphere, blazes at 1 to 2 million Kelvin. It's one of the biggest unsolved mysteries in astrophysics. Wait. You're telling me it gets hotter as you go away from the star? That's insane. That violates everything I know about heat. It seems to, doesn't it? But the corona isn't heated by thermal radiation from below. It's heated by magnetic energy. The star's magnetic field, twisted and tangled by the churning convection below, snaps and reconnects in the corona, releasing enormous amounts of energy. It's like 1,000,000 lightning strikes per second, all heating this thin plasma to incredible temperatures. But here's the saving grace that might buy Chowder an extra few seconds of survival. The corona is incredibly tenuous. At this altitude, there might only be 1 billion particles per cubic centimeter. That sounds like a lot, but Earth's atmosphere at sea level has about 30 million trillion particles in the same volume. The corona is basically a hot vacuum.
90,000 kilometers to the surface. The instruments are going haywire. Temperature outside is reading, this can't be right, 1.2 million Kelvin? But inside the cabin, it's only 97 degrees Celsius. That's because temperature and heat are different things, Chowder. Temperature measures the average kinetic energy of particles, how fast they're moving. Heat measures the total thermal energy transferred. The particles in the corona are moving at incredible speeds, thousands of kilometers per second, but there are so few of them that they can't transfer much heat to the spacecraft. Okay, so I'm not instantly vaporized. That's good news, right? Don't celebrate yet. You're descending, and with every kilometer, the atmosphere is getting denser. Those sparse particles are becoming less sparse, and your spacecraft is beginning to compress and heat the plasma in front of it, just like a meteor entering Earth's atmosphere. 70,000 kilometers. There's a glow forming in front of the ship, a bright region where we're plowing through the corona. It's like a shock wave of light. That's a bow shock, Chowder. The spacecraft is now moving fast enough, over 50,000 kilometers per hour, and accelerating, that it's compressing the coronal plasma in front of it. That compression heats the plasma even further, creating a luminous shock wave. The hull temperature is now exceeding 600 degrees Celsius in some areas. That's hot enough to glow a dull red if you could see it through the plasma. The heat shields have exceeded their rated capacity and are now ablating rapidly. Material is streaming off the ship in a glowing tail. 50,000 kilometers. Cabin temperature 112 degrees Celsius. I can't breathe properly. The air is too hot. My suit's cooling system is maxed out. I'm seeing spots in my vision. At 112 degrees Celsius, the air temperature is above the boiling point of water. The moisture in Chowder's lungs would be evaporating. His body's cooling mechanism, sweating, has completely failed because the surrounding air is too hot to allow evaporation. He's cooking from the inside out. His heart rate has spiked to over 160 beats per minute. Blood pressure is dangerously high. Core body temperature is climbing toward 42 degrees Celsius, the point where proteins begin to denature and brain damage becomes irreversible. 30,000 kilometers. The readings don't make sense anymore. Everything is failing. Hull integrity warnings, the view screen is... The stars, all I can see. It's everything. Orange and yellow and white, churning, rising, falling. The spacecraft is beginning to come apart. Seams are splitting. Electronics are frying. The outer hull plating, designed for the cold vacuum of deep space, is warping and buckling under thermal stress. Pieces are breaking off, vaporizing instantly in the million-degree plasma. 20,000 kilometers above the photosphere, the density has increased enough that the spacecraft is experiencing real atmospheric drag. It's decelerating slightly, but that just means it's spending more time in this hellish environment, absorbing more heat. I can see structures in the corona, loops and arcs of plasma following magnetic field lines. They're beautiful, like bridges of light connecting different parts of the star. Some are stable, some are erupting, exploding outward in massive coronal mass ejection. 1 billion tons of plasma accelerated to 1 million kilometers per hour by a magnetic field that just snapped and reconnected violently. It tears past the spacecraft, bathing it in even more intense radiation and heat. Systems failure, total failure, life support offline, navigation offline, the hull is breaching. 10,000 kilometers above the photosphere, the temperature outside has paradoxically dropped to about 100,000 Kelvin. We're leaving the corona and entering the chromosphere, the transition region between the star's outer and inner atmosphere. But for astronaut Chowder, this is the final descent.
The chromosphere. In Greek, it means color sphere, named for the beautiful pinkish-red glow it produces during solar eclipses. That color comes from hydrogen alpha emission, hydrogen atoms being excited and then releasing photons at a specific wavelength. But there's nothing beautiful about it when you're falling through it. Astronaut Chowder. Can't breathe. Hull breach. Cabin at 150 degrees. Everything's red. The chromosphere is denser than the corona, about 1,000 times denser, though still far more tenuous than Earth's atmosphere. The temperature here sits around 10,000 to 20,000 Kelvin in the upper regions, climbing toward the photosphere below. At this density and temperature, the spacecraft doesn't stand a chance. The heat shield is gone, completely vaporized. The outer hull is peeling away in layers, each layer flashing into plasma as it's exposed to the stellar atmosphere. The spacecraft is leaving a trail of glowing debris, atoms of aluminum, titanium, and carbon, all stripped from the dying vehicle. Astronaut Shouter: 5,000 kilometers. I can see it. The surface. It's like an ocean. Waves of fire. What Shouter is seeing are spicules, jets of plasma shooting up from the photosphere below, some reaching 5,000 to 10,000 kilometers high. They last only a few minutes before falling back, but there are thousands of them at any given moment, creating a forest of fire reaching up through the chromosphere. The cabin temperature has exceeded 200 degrees Celsius. At this temperature, the spacecraft's interior is an oven. Plastic components are melting, electronic displays have failed. The structural integrity of the hull is measured in seconds. Astronaut Shouter: Mom, I can't. It's too hot. Everything hurts. Astronaut Shouter's spacesuit has failed. The cooling system melted minutes ago. His skin is covered in second and third degree burns. The air temperature is now high enough that each breath sears his lungs. He's on the edge of consciousness, his brain beginning to shut down as his core temperature exceeds 45 degrees Celsius. 2,000 kilometers above the photosphere. The density has increased to the point where we can finally call this an atmosphere by conventional standards, though it's still thinner than Earth's atmosphere at 100 kilometers altitude. But the temperature is now 30,000 Kelvin, hot enough to ionize most elements, hot enough to break molecular bonds, hot enough that matter exists only as plasma, a fourth state of matter where electrons have been stripped from atoms. Astronaut Shouter: The light. Everything is light, and I'm part of it now. 1,000 kilometers. The spacecraft has ceased to exist as a coherent object. It's now a cloud of vaporized metal and organic compounds, expanding and mixing with the stellar atmosphere. The atoms that made up the hull, the computers, the life support systems, they're all plasma now, indistinguishable from the star itself. An astronaut Shouter. Silence for a beat. Astronaut Shouter's body has vaporized. Every molecule, every atom that made up his bones, his blood, his brain has been torn apart by thermal energy. The chemical bonds that held his DNA together have broken. The proteins that formed his cells have disintegrated. He exists now only as a cloud of constituent elements: carbon, hydrogen, oxygen, nitrogen, calcium, phosphorus. These atoms are being carried by convection currents, mixing with the star's atmosphere. But we're not done, because those atoms, Shouter's atoms, are still falling, pulled by gravity toward the core, toward the place where stars forge the very elements of existence. We're about to reach the photosphere, the surface of the K-type star. Though calling it a surface is misleading. There's no solid ground here, no boundary you could stand on. The photosphere is simply the layer from which photons can finally escape into space. Below this point, the star is opaque. Above it, space becomes transparent. This is what we see when we look at a star from Earth, the light from its photosphere. The temperature here is about 4,000 to 5,000 Kelvin, roughly 4,000 to 5,000 degrees Celsius. That's 3/4 the temperature of our sun's surface. It's cooler, which is why K-type stars glow orange instead of yellow-white. But cooler is a relative term. 4,000 degrees is still hot enough to vaporize every element in the periodic table, except for a few exotic exceptions.
Tungsten would be a liquid here, carbon would be a gas, water would be, well, water can't exist in molecular form at all. It would be disassociated into hydrogen and oxygen plasma. What would you see if you could somehow survive here with your vision intact? You'd see convection cells, granulation patterns extending as far as the eye could reach. Each cell is a massive bubble of hot plasma rising from below. The center of each cell glows brighter, about 100 Kelvin hotter than the edges because it's fresh material from deeper in the star. These cells are in constant motion. They rise, expand, cool slightly, then sink back down at the edges in a continuous cycle. Each cell lasts only a few minutes before dissolves and reforms. The entire surface is boiling, churning, seething with motion. Scattered across the photosphere, you'd see darker regions, star spots. These are areas where magnetic field lines have burst through the surface, creating regions of cooler plasma. They look dark only by contrast. They're still radiating at about 3,000 Kelvin, bright enough to vaporize you instantly. Around the star spots, you might see bright faculae, regions where magnetic fields have heated the plasma even further. And if you're unlucky, you might witness a stellar flare, a massive eruption where magnetic field lines snap and reconnect, releasing as much energy as 1 billion nuclear bombs in a matter of seconds. The density at the photosphere is incredibly low by Earth standards, about 1/10,000th the density of sea level air, but it's 1 billion times denser than the corona we passed through earlier. That density, combined with the 4,000-degree temperature, creates enormous pressure. The atoms that were once astronaut chowder are experiencing about 1,000th of Earth's atmospheric pressure. That doesn't sound like much, but at these temperatures, pressure and density are sufficient to keep the plasma in a state of equilibrium, neither collapsing nor exploding, just flowing in massive convection currents.
Those atoms, carbon from Chowder's body, nitrogen from his DNA, calcium from his bones, are being swept downward now. The convection current has caught them in the downflow at the edge of a granulation cell. They're sinking, being pulled deeper into the star by gravity in convective motion. The temperature is increasing, 5,000 Kelvin, 6,000. The pressure is climbing too. What was a tenuous plasma is becoming denser, more compressed. The atoms are colliding more frequently, exchanging energy, being accelerated by the increasing temperature. At this depth, about 500 kilometers below the visible surface, the temperature reaches 8,000 Kelvin. The density is about 1/10 that of water. The plasma here is opaque to light. Photons generated in the core take thousands of years to random walk their way outward to this point, and then suddenly, in the last few hundred kilometers, they break free and race into space at light speed. But we're not escaping. We're descending. 1,000 kilometers below the photosphere, 10,000 Kelvin. The pressure is now 1/10 of Earth's atmospheric pressure at sea level and climbing. The convection patterns are massive here, currents thousands of kilometers wide, flowing at speeds of several kilometers per second. Chowder's atoms are being scattered, separated. A carbon atom that was part of his heart is now hundreds of kilometers from a hydrogen atom that was in his brain. They're individual particles now, no longer bound into molecules or compounds, just free ions in an ocean of plasma. 2,000 kilometers deep, 15,000 Kelvin. The energy here is so intense that the plasma glows in ultraviolet, if only there were anyone to see it. The density is now similar to water, 1 gram per cubic centimeter. And we're approaching the boundary, the transition from photosphere to convection zone, the convection zone. This is where the real bulk of the star conducts heat from the core to the surface. In a K-type star, the convection zone extends from just below the photosphere all the way down to about 70% of the star's radius. That's over 200,000 kilometers of churning, flowing plasma. Here, energy transport changes. In the radiative zone below, energy moves via photons being absorbed and re-emitted by atoms. But in the convection zone, the plasma itself carries the energy.
Hot plasma rises, cool plasma sinks, creating massive circulation patterns, the stellar equivalent of Earth's atmospheric Hadley cells, but on a scale that defies comprehension. The temperature is now climbing rapidly, 20,000 Kelvin, 50,000, 100,000. The deeper we go, the hotter it gets. In the pressure is becoming immense. At 100,000 kilometers depth, the pressure is about 100 times Earth's atmospheric pressure at sea level. The temperature is 500,000 Kelvin. The density is 10 times that of water. At these conditions, the atoms that were chowder are completely ionized. Every electron has been stripped away. What remains are bare nuclei, carbon-12 nuclei with 6 protons and 6 neutrons, hydrogen nuclei that are just single protons, oxygen-16 nuclei, nitrogen-14 nuclei. These nuclei are in constant violent motion. They're colliding with each other millions of times per second, bouncing off in random directions. The kinetic energy is so high that if any of these nuclei tried to form atoms by capturing electrons, the electrons would immediately be knocked loose again by the next collision. 150,000 kilometers deep. Temperature 1 million Kelvin. Pressure 10,000 atmospheres. Density 100 times that of water. The convection currents here move slowly by human standards, maybe a few meters per second, but they're carrying entire Earth masses of plasma at a time. The magnetic field lines are tangled and twisted by this motion, creating complex topologies that eventually manifest as star spots and flares on the surface far above. What would happen to a human body here? There is no wood, there is no body, there never could be. At these temperatures and pressures, molecular bonds are meaningless concepts. The only structures that exist are atomic nuclei and free electrons, all in constant thermal motion. The protons that were in Chowder's DNA, the carbon nuclei that formed his proteins, the iron that carried oxygen in his blood, they're all just charged particles now, indistinguishable from the star's own material. We're approaching the base of the convection zone, 200,000 kilometers below the surface. The temperature is reaching 2 million Kelvin. The pressure is 100,000 atmospheres. The density is 500 grams per cubic centimeter, half the density of iron. At this depth, we're at about 30% of the way to the core, measured by radius, but we're still 75% of the way by mass. Most of the star's mass is concentrated in the core. And now we cross another boundary. Below this point, convection stops. The plasma is too dense, the pressure too high, the temperature gradient too shallow for convection to be efficient. Energy transport switches back to radiation, photons being absorbed and re-emitted by ions. We're entering the radiative zone, and beyond that, the core, the place where stars forge the universe. The core, the heart of the star, the forge of elements, the place where hydrogen becomes helium, where mass becomes energy, where Einstein's famous equation E equals mc squared transforms matter into the light that illuminates galaxies. At the center of our K-type star, the temperature has reached 10 to 15 million Kelvin. That's 10 to 15 million degrees Celsius. At these temperatures, atomic nuclei are moving so fast that when they collide, they can overcome the electromagnetic repulsion that normally keeps positive charges apart. The pressure is unimaginable, 2 billion times Earth's atmospheric pressure. That's the weight of the entire star pressing inward, held at bay only by the outward pressure of the insanely hot plasma and the radiation generated by fusion. The density is 150 grams per cubic centimeter, 20 times denser than iron, despite being made primarily of hydrogen. What happens here is the process that powers stars. It's called the proton-proton chain reaction, and it goes like this. 2 hydrogen nuclei, just 2 protons, collide with enough energy to stick together briefly. One of them undergoes beta plus decay, transforming into a neutron and releasing a positron and a neutrino. Now you have a deuterium nucleus, 1 proton, 1 neutron. That deuterium nucleus collides with another proton, forming helium-3, 2 protons, 1 neutron, and releasing a gamma-ray photon. 2 helium-3 nuclei collide, forming helium-4, 2 protons, 2 neutrons, and spitting out 2 protons to start the cycle again.
The result? 4 hydrogen nuclei have been fused into 1 helium nucleus. And here's the magic. The helium nucleus has slightly less mass than the 4 hydrogens did, about 0.7% less mass. That missing mass? It's been converted into energy, into the gamma-ray photons and the kinetic energy of the particles and the neutrinos that escape the star, into the heat and pressure that keep the star from collapsing, into the light that eventually emerges from the photosphere and travels across space to warm planets and give rise to life. Every second, our K-type star converts about 200 million tons of hydrogen into helium. In every second, about 500,000 tons of that mass vanishes, transformed into pure energy, according to E equals mc squared. That's the power of nuclear fusion. That's the engine of stars. And here, in the core of this star, the atoms that were once astronaut Chowder are participating in this cosmic alchemy. The hydrogen nuclei that were once in his body, in his water, in his proteins, in his DNA, they're colliding with other nuclei now. Some of them might undergo fusion themselves, joining together to form deuterium or helium-3. The energy released would add to the inferno, indistinguishable from the fusion reactions happening around them. The carbon nuclei, the oxygen nuclei, the nitrogen, these don't undergo fusion in a K-type star. The temperature isn't high enough, but they're here in the core, bathed in radiation, colliding with other particles, slowly being pushed outward by radiation pressure and convection over millions of years. Eventually, in millions or billions of years, some of Chowder's atoms will work their way back to the surface. They'll be carried by convection currents back up through the radiative zone, through the convection zone, to the photosphere. There, they'll finally escape. Some might be blown off in a stellar wind. Others might wait until the star dies, billions of years from now, when it swells into a red giant and gently puffs off its outer layers as a planetary nebula. Those atoms will drift into space. They'll join clouds of gas and dust. Eventually, they might become part of a new star system, or a planet, or a comet. Or, in the vastness of cosmic time, they might become part of another living being. Because that's the ultimate truth that Chowder has discovered, not through understanding, but through experience. We are made of star stuff. Carl Sagan said it, and he was right. The atoms in our bodies were forged in the cores of ancient stars, stars that died before our sun was born. And when we die, those atoms return to the cosmos, ready to be recycled again. Astronaut Chowder fell into a star. His body was destroyed, vaporized, atomized, disintegrated at the most fundamental level. But his atoms, the matter that made him, they're eternal. They're part of the star now, part of the fusion fire, part of the light that will shine across space for billions of years to come. In a way, Chowder achieved immortality. Not the immortality of memory or legend, but physical immortality. His atoms will exist until the heat death of the universe itself. That's the fate of anyone who falls into a star. Complete destruction, total transformation, ultimate recycling, and a strange, beautiful form of cosmic eternity. Okay, let's take a breath, a normal room temperature breath, and talk about the actual science behind what we just experienced with astronaut Chowder. First question, could a human actually survive any part of this journey? Not even close. Not with current technology, not with any foreseeable technology. The closest we've ever sent a spacecraft to a star is the Parker Solar Probe, which in 2021 actually touched the sun's corona, passing through it at about 9 million kilometers from the surface. It experienced temperatures of about 1 million Kelvin, though its heat shield kept the instruments at room temperature.
But the Parker Solar Probe doesn't try to descend to the surface. It makes quick passes through the outer corona and then escapes back to safer distances. It's built with a 12-centimeter thick carbon composite heat shield and weighs only about 700 kilograms. A spacecraft large enough to carry a human, with life support systems and enough shielding to protect against radiation and heat. It would need to be so massive, so heavily armored, that no rocket could lift it. And even then, it couldn't survive past the corona. The radiation alone would be lethal. At 1 million kilometers from a K-type star, you're receiving thousands of times the radiation dose that causes acute radiation syndrome. Your DNA would be shredded, your cells would die. Even if you somehow survive the heat, the radiation would kill you. And the heat? There's no material we know of that can withstand continuous exposure to 4,000 degrees Celsius. We can build materials that handle that temperature briefly, ceramic heat shields on spacecraft, for example, but they're single-use, and they only buy you seconds or minutes. So how do we actually study stars? From a distance, very safely, with telescopes. We use spectroscopy, analyzing the light from stars to determine their temperature, composition, density, and motion. When we split starlight into its component wavelengths, we see absorption lines, dark lines where specific elements have absorbed specific wavelengths. Each element has a unique spectral signature, so we can figure out what stars are made of without ever getting close. We use photometry, measuring the brightness of stars over time. When a planet passes in front of a star, the star dims slightly. By measuring that dimming, we can detect exoplanets and even determine their size. We use interferometry, combining light from multiple telescopes to achieve incredibly high resolution, allowing us to actually see features on the surfaces of nearby stars. And we use space-based observatories like the Hubble Space Telescope, the James Webb Space Telescope, and dedicated stellar missions like the European Space Agency's Gaia satellite, which is mapping the positions and properties of over 1 billion stars. Now, let's talk about K-type stars specifically and why they're so important. K-type stars are what astronomers call Goldilocks stars when it comes to habitability. They're more stable than M-type red dwarfs, which tend to have violent flares that would sterilize nearby planets. They're longer-lived than G-type stars like our Sun, giving life more time to evolve. And they're common, billions of them in our galaxy alone. The habitable zone around a K-type star is closer than Earth is to the Sun, typically about 0.4 to 0.8 astronomical units, compared to Earth's 1 AU, but that zone is stable for 15 to 30 billion years, compared to our Sun's 10 billion year lifespan. Some scientists think K-type stars might be the most likely places in the universe to find complex life. They're the sweet spot, not too hot, not too cold, not too volatile, not too short-lived.
If we compare what astronaut Chowder experienced to what would happen in other types of stars, in an M-type red dwarf, the smallest and coolest true stars, the surface temperature would be only 2,000 to 3,000 Kelvin. You'd last a little longer before vaporizing, but red dwarfs have violent magnetic activity and emit more X-rays relative to their visible light, so the radiation would get you faster. In a G-type star like our Sun, the surface temperature is about 5,700 Kelvin. You'd vaporize faster, and the corona would be even more intense, up to 3 million Kelvin in active regions. In an F-type star, hotter and more massive than the Sun, you'd experience temperatures up to 7,500 Kelvin at the surface and even more intense radiation. And if you fell into an O-type or B-type blue giant, the surface temperatures exceed 30,000 Kelvin. You'd be vaporized while still millions of kilometers away, just from the intensity of the ultraviolet radiation. The core temperatures vary too. Red dwarfs fuse hydrogen at only about 2 to 3 million Kelvin, just barely hot enough for fusion. Massive O-type stars have core temperatures exceeding 40 million Kelvin and burn through their fuel in only a few million years before exploding as supernovae. But here's the beautiful thing. It's in those supernova explosions that the heavy elements are made: carbon, oxygen,
Nitrogen, iron, gold, uranium, all the elements heavier than helium are forged either in the cores of massive stars or in the supernova explosions themselves. So when astronaut Chowder fell into that K-type star, he joined the cosmic cycle. The iron in his blood was made in a supernova billions of years ago. The carbon in his DNA was forged in the core of some ancient star. And now, those atoms are part of a new star, waiting to be recycled again when that star eventually dies. It's sobering, it's beautiful, it's the reality of the universe we live in. We're not separate from the cosmos, we're part of it, made by it, powered by it, and eventually, we return to it. So, we've done it. We've taken the ultimate journey with astronaut Chowder, from the cold vacuum of space, through the ghostly corona, past the seething photosphere, down through the convection zone, and into the nuclear furnace of the core. We've experienced what happens when human matter meets stellar matter, and the answer is transformation. Complete, total, fundamental transformation. Astronaut Chowder didn't survive. No one could. But in a way, he achieved something profound. He became one with a star. His atoms joined the fusion fire. His matter became energy. His physical form was destroyed, but his constituent parts became eternal. You know what? I think I'm okay with that. I mean, I'm not actually okay with it because I'm theoretically vaporized, but there's something beautiful about becoming part of something so vast, so powerful, so eternal. My atoms will shine across space. They'll warm planets I'll never see. Maybe billions of years from now, they'll be part of someone else looking up at the stars and wondering what it would be like to touch one. And that's the lesson, isn't it? We're all temporary. Our bodies, our identities, our consciousness, they're brief patterns in the cosmic dance. But the matter we're made of, that's eternal. Those atoms have been on a journey for billions of years, and they'll continue for billions more. You are literally made of stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, they were forged in stellar cores and scattered by supernova explosions. And when you die, those atoms will continue their journey. K-type stars, those orange dwarfs we explored today, might be the best homes for life in the universe. Stable, long-lived, gentle by stellar standards. Somewhere out there, orbiting a K-type star, there might be a planet with oceans and continents, with an atmosphere, with life looking up at their orange sun and wondering if they're alone. And maybe, just maybe, those beings are made of atoms that once belonged to a star just like the one we fell into today. We're all connected through the cosmic recycling program. If you enjoyed this journey into the heart of a star, here's how you can support the Cosmic Atlas. Hit that subscribe button. We're exploring the most extreme environments in the universe, from black holes to neutron stars to the edge of the observable universe itself. You don't want to miss what's coming next. Smash that like button. It tells YouTube that you want to see more science content like this, and it helps us reach more cosmic explorers like you. Share this video. Send it to anyone who loves space, anyone who's curious about the universe, anyone who's ever looked at a star and wondered what it would be like to touch one. Spoiler, it would be very brief and very hot. And drop a comment below. Tell me, what cosmic destination should we explore next? Should we fall into a black hole and experience spaghettification? Should we visit a neutron star and feel the crushing gravity? Should we travel to the edge of a supernova and witness the most violent explosion in the universe? Let me know in the comments. Your suggestions drive this channel. And maybe suggest somewhere I can survive for more than 10 minutes? Just a thought. I'd like at least one mission where I don't become plasma. No promises, Chowder, but we'll see what we can do. Coming up on the Cosmic Atlas, we're going to explore what happens if you fell into a black hole. Not just any black hole, a supermassive black hole at the center of a galaxy. We'll experience time dilation, gravitational tides, and the ultimate question, what lies beyond the event horizon? And after that, we're visiting a magnetar, the most magnetic object in the universe, where the magnetic field is so intense it would tear your atoms apart from 1,000 kilometers away. I'm starting to think you just enjoy watching me suffer cosmically. But okay, I'm in. Someone's got to do it. That's the spirit, Chowder. This has been the Cosmic Atlas. I'm your host, reminding you to look up at the stars tonight. Those points of light, they're nuclear furnaces, fusion reactors, element forges. They're billions of years old, and they'll shine for billions more. And you're made of their remains. You're star stuff, contemplating stars. You're the universe experiencing itself. Never forget how amazing that is. And never forget, don't fall into a star. Just don't do it. Trust me on this one. Sound advice, Chowder. Until next time, Cosmic Explorers, keep looking up, keep asking questions, keep exploring. The universe is waiting.